Welcome to the deep dive. Today, we're tackling the world of algorithmic thinking, how computer scientists solve problems, basically.
Exactly, and we're using Algorithmic Thinking, a problem-based introduction by Daniel Zingaro as our guide. It's a great book for this.
Yeah, we've dug into it to pull out the key ideas. The goal is to give you a kind of shortcut to understanding how clever algorithms and data structures work without getting totally bogged down.
Right. Think of it as, well, grasping the core principles. The book teaches through problems, which is a really effective way to learn this stuff. We'll cover things like hash tables, heaps, recursion, dynamic programming.
The fundamentals.
Fundamentals, yeah. And also graph algorithms.
And it connects these to real challenges, right? Like programming competitions.
It does. It mentions IOI, CCO, ACM, ICPC. So these aren't just abstract ideas. They're tools people use to solve tough competitive problems.
Okay, so our mission today, extract those key insights, those aha moments. Show the elegance, the efficiency gains you get from thinking algorithmically. We'll use relatable examples. Keep it focused. Ready to dive in.
Let's do it. Maybe start with hash tables.
Sounds good. Fast searching, right? That's the main idea.
That's the core concept. They're built for speed when you need to find something quickly. It's fundamental in a lot of applications.
Okay, so where do they really make a difference? Give me an example.
Well, the book has a neat one called the snowflake problem. Imagine you have loads of snowflakes, each described by 6 numbers, like the lengths of their arms.
Okay, 6 numbers per snowflake.
Right. And 2 snowflakes are identical if their 6 numbers match, or if you can rotate or flip one sequence to match the other.
Ah, okay. So comparing every single snowflake to every other one and checking all those rotations and reflections, that sounds like it could get really slow, really fast, especially with lots of snowflakes.
Exactly. That's the brute force way, and it would grind to a halt. But with a hash table, the idea is to create a single, unique hash value, like a fingerprint, for each snowflake that represents all its possible forms, rotations, reflections, everything.
You condense it down?
You condense it down into one number, essentially. Then you store that hash in the table. When a new snowflake comes along, you calculate its unique hash and just look it up in the table.
Ah, so instead of tons of comparisons, it's just one quick check. Is this hash already here?
Precisely. It turns a complex comparison into a near-instant lookup. Makes a huge difference for big data sets.
Clever. What's another example?
Another good one is finding compound words in a dictionary list. So you have a list of words, and you want to find which ones are made by sticking 2 other words from the same list together.
Like blueprint, if blue and print are also in the list.
Exactly.
Okay, so again, the slow way would be, for every word, try splitting it everywhere. And then check if both halves are in the dictionary.
Yep.
That's the naive way. If you have n-words, you're looking at something like ON2, time complexity. Lots of checking.
Which means it gets exponentially slower as the list grows.
Right, but if you put all the dictionary words into a hash table first.
Ah, I see where this is going.
Yeah. Then when you split a potential compound word, checking if the 2 pieces are valid words becomes super fast. It's essentially O1 on average per lookup.
So the whole problem goes from ON2 down to...
Down to basically ON, a massive speed up.
That really drives home the efficiency game. It's the difference between, I don't know, searching a whole library card catalog versus just knowing the exact shelf the book is on.
That's a good way to put it. And the book also touches on collisions.
Right. What happens if 2 different snowflakes, say, accidentally get the same hash value?
Yeah, it happens. A common solution is using linked lists. Each slot or bucket in the hash table can hold a list of items that hashed that same value. So if there's a collision, you just add the new item to the list in that bucket. Got it. So you might have a short list to check sometimes, but it's still way faster than comparing everything.
Much faster. There are other ways too, like open addressing, but linked lists are a pretty standard approach.
Okay, fascinating stuff. Let's shift gears. Recursion and trees. The book links these, right?
It does. Recursion is this idea of solving a problem by using solutions to smaller versions of the exact same problem.
Breaking it down to self-similar pieces.
Exactly. And trees are data structures with a natural hierarchy, like a family tree or an org chart.
So how do they fit together?
Well, trees are self-similar. A big tree is made up of smaller subtrees, which are themselves trees. So recursion is a very natural, often elegant way to work with them. You define what to do for the simplest case, like a single leaf.
The base case.
The base case, right. And then you define how to handle a bigger tree by recursively applying the same logic to its smaller parts, its subtrees.
Makes sense. What's a problem example?
The book uses one called Halloween Hall. Imagine a map laid out as a binary tree. Nodes are either houses with candy or just intersections.
Okay.
The goal is to find the minimum streets to walk to get all the candy, and also the total candy collected. Recursion works beautifully here.
How so?
Well, if you're at a house node that's a base case, you just return the candy amount. If you're at an intersection, the recursive step is to call the same function on its left child and its right child. You then combine the results, like summing the candy from both subtrees.
And you can figure out the streets needed recursively, too.
Yeah, you'd calculate the streets needed for the left and right subtrees and combine that, adding the streets connecting the current intersection.
Okay, I can picture that. Exploring down the branches, what's another tree problem?
There's the descendant distance problem. This time, it's a general tree, so nodes can have lots of children, not just two.
Right.
The task is, for every node, find how many of its descendants are exactly cabals below it.
So how many grandchildren or great-grandchildren, etc.?
Kind of, yeah. The recursive logic is pretty neat. If D1, the answer is just the number of direct children. That's like a base case.
Okay.
If D is bigger than 1, you ask each of your children, how many descendants do you have at distance D1? Then you just sum up all the answers you get back from your children.
Ah, so each node pushes the question down one level to its kids. It's like a ripple effect.
Exactly. It elegantly breaks down the problem. The key takeaway is how recursion lets you handle these self-similar structures, like trees, really cleanly.
But recursion isn't always the most efficient way, is it? The book mentions optimization.
That's a crucial point. Sometimes a straightforward recursive solution can end up doing the same calculations over and over again, especially if the smaller subproblems overlap.
Like calculating the same value multiple times in different parts of the recursion.
Precisely. And that can lead to exponential slowdowns. That's where memoization and dynamic programming come in. They're techniques to avoid that redundant work.
Okay, memoization and dynamic programming. What's the difference? Are they the same thing?
They're related, aiming for the same goal, avoid recomputation, but they approach it slightly differently. Memoization is usually top-down. You write your recursive function, but you add a cache, like a lookup table.
A memory.
Yeah, a memory. Before making a recursive call, you check, have I already solved this exact subproblem? If yes, you just return the stored answer. If no, you compute it, store it, and then return it.
Got it. So it's recursion plus caching. What about dynamic programming?
Dynamic programming, or DP, is typically bottom-up. You figure out the smallest possible subproblems, solve them first, and store their results, usually in an array or table. Then you systematically build up solutions to bigger and bigger subproblems using the results you've already stored. It's often done iteratively, with loops rather than recursion.
Okay, so memoization is like lazy computation within recursion. DP is more like building the solutions from the ground up, step by step. Can you give an example?
Sure, the burger fervor problem is perfect. Let's say you have a time limit T, and two types of burgers take minutes and n minutes to cook, respectively. You want the maximum number of burgers you can cook within time T.
Okay.
A naive recursive solution might try every combination. Cook burger M, then recursively solve for time T, or cook burger N, recursively solve for Tn.
I can see how that would branch out wildly and recalculate things for the same remaining time.
Exactly. It explodes. With memoization, you'd store the best answer for each possible remaining time. If you need the answer for, say, 10 minutes left, you calculate it once and store it. The next time you hit 10 minutes left via a different path, you just retrieve the stored answer.
And the DP approach.
With DP, you'd likely create an array, say DP, where dpi stores the max burgers you can make in exactly ORI minutes. You'd fill this array starting from dp0, then dp1, dp2, and so on, up to dpt. To calculate dpi, you'd look back at previously computed values, like dpm and dpm, and use those to figure out the best value for dpi.
So you build the solution iteratively, ensuring you never recalculate.
Precisely. Both techniques turn potentially exponential problems into much faster, often polynomial or linear time solutions, just by storing and reusing results. Essential tools.
Really powerful optimization.
Yeah.
Okay, let's switch gears again. Graphs. Modeling relationships, right? And algorithms like BFS and Dijkstra's.
Exactly. Graphs are incredibly versatile. Nodes represent things, edges represent connections or relationships between them. Think social networks, maps, the internet.
Lots of things.
Tons. And breadth first search, BFS, is one way to explore a graph. It starts at a node and explores outwards layer by layer. visits all immediate neighbors, then their neighbors, and so on.
Like ripples in a pond?
Good analogy. Dijkstra's algorithm is different. It's for weighted graphs where edges have costs or lengths. It finds the shortest path from a starting node to all other nodes in the graph.
So BFS is about minimum number of steps or links. Dijkstra's is about minimum total cost or distance.
You got it.
Examples. Where would you use BFS?
The book gives the knight chase problem on a chessboard. Can a knight capture a pawn in, say, 3 moves or less? You model the board as a graph. Squares are nodes, possible knight moves are edges. Since each move counts as one step, BFS is perfect. You start BFS from the knight square. Level 1 is all squares reachable in 1 move. Level 2 is all squares reachable in 2 moves. You just see if the pawn square shows up within the allowed number of levels.
Makes perfect sense. Layer by layer exploration. And Dijkstra's.
Think grandma's shortest path. You have a map, cities are nodes, roads are edges with distances. Dijkstra's finds the shortest route from you to grandma. The book even shows how to modify it to count how many distinct shortest paths exist.
Oh, interesting.
Another example is mice maze. Mice start in a maze, there's an exit and a time limit. How many mice can escape?
Okay. How does Dijkstra's help there?
You model the maze as a graph, cells are nodes, time to move between cells is the edge weight. You run Dijkstra's from the exit back to all possible starting cells. This tells you the minimum time for a mouse starting at any cell to reach the exit. Then you just count how many mice can make it within the time limit.
Ah, clever. Running it backwards from the goal. It's amazing how these core algorithms apply to such different scenarios.
It really is. That's the power of abstraction. Model the problem as a graph, and suddenly you have these powerful tools ready to use.
Okay, next up, union find. Managing disjoint sets. What does that mean?
Think of it like managing groups or clubs where no one can be in more than one group at a time. Disjoint sets are just collections like that.
Okay.
Union find is a data structure designed specifically to do 2 things really fast. Union, which merges 2 separate groups into one.
Like if 2 clubs merge.
Exactly. And find, which tells you which group a particular person belongs to, usually by returning a representative element for that group.
So grouping things and checking membership efficiently. Where is that useful?
The book uses a social network example. Imagine tracking friendships. Everyone starts in their own group set of 1. When Alice and Bob become friends, you union their sets.
They're now in the same circle.
Right. Later, if you want to know if Alice and Charlie are connected, maybe through a chain of friends, you do a find on Alice and a find on Charlie. If they return the same representative, they're in the same connected community.
And this is faster than, say, tracing all the friend links.
Way faster, especially for large networks. The magic comes from optimizations the book mentions, like union by size and path compression.
Briefly, what do those do?
Union by size means when merging 2 groups, you always make the smaller group join the larger one. This helps keep the structure representing the sets from getting too deep and stringy. Path compression happens during a find. When you look up someone's group, you make everyone you passed on the way up point directly to the ultimate representative. This flattens the structure dramatically over time.
So it makes future find operations even faster.
Exactly. With these tricks, a sequence of union and find operations becomes incredibly efficient, almost constant time on average per operation. Very powerful for connectivity problems.
Cool. Okay, let's talk searching again, but specifically in sorted data. Binary search.
Binary search. A classic. Super efficient for finding something in a sorted list.
How does it get that efficiency?
By repeatedly cutting the search space in half. You look at the middle element of your sorted list. Is it the target? Great, you're done. Is your target smaller? Then you only need to search the left half. Is it larger? Only search the right half.
Like guessing a number between 1 and 100 and someone tells you higher or lower.
Exactly like that. Each guess cuts down the possibilities significantly.
And because you have the search space each time, it's way faster than checking every single item one by one, especially for big lists.
Absolutely. Checking one by one is linear search, O1N. Binary search is O-log, logarithmic time. For 1 million items, linear search might take 1 million checks in the worst case. Binary search, maybe 20 checks.
Huge difference.
Hmm.
What are some non-obvious applications from the book?
Well, there's the feeding ants problem. You have this terrarium structure, liquid flows down, splitting at junctions. You need to find the minimum liquid at the top to feed all the ants at the bottom leaves.
Okay, how is that binary search?
You can binary search on the amount of liquid, pick an amount. Can you feed all the ants with this much? You can figure that out with a check function. If yes, maybe you can do it with less, so you try the lower half of your liquid range. If no, you need more, so you try the upper half.
Ah, because the can I feed them property is monotonic.
Hmm.
If X amount works, any amount greater than X also works.
Precisely. That monotonicity lets you use binary search. The book also mentions removing rocks. You have rocks on a line, you remove some, and you want to maximize the minimum distance between any two remaining rocks.
Okay.
You can binary search on the possible minimum distance. For a given distance, you check, can I remove the allowed number of rocks and ensure all remaining rocks are at least apart? Again, it's that monotonic property that enables binary search.
So binary search is powerful not just for finding exact values, but for optimizing parameters too, as long as there's that predictable relationship.
Exactly. A very versatile tool when you have sorted data or that monotonic property.
All right, now for something that sounds a bit more specialized. Segment trees. What's the deal with those?
Yeah, segment trees are pretty neat. They're specifically designed to handle range queries on an array efficiently.
Range queries. Like,
Yeah.
find the sum of elements from index 10 to 20, or the maximum value in that range.
Exactly that. Sum, minimum, maximum, or sometimes more complex things over a specified range or segment of an array. And critically, they usually also let you update individual elements in the array efficiently too.
So if I have a big array and I'm constantly asking what's the max value between here and here,
Hmm.
and also changing values occasionally, a segment tree helps.
Immensely. Instead of scanning that range every single time for your query, which would take linear time depending on the range size, a segment tree lets you do most range queries and single updates in O log n time, where n is the total size of the array.
Logarithmic time again.
Yep.
Much faster for large arrays and mini queries.
Definitely. You pay a bit of cost up front to build the tree, but then the queries and updates are fast.
What are some examples from the book?
It mentions using them for building trees. Trees are a kind of balanced search tree, and constructing them can involve repeatedly finding the element with the highest priority within a certain range. Segment trees are great for that range maximum query.
Okay.
Another one is maximum sum of two elements in a range. A segment tree can be built to store not just the max or sum, but enough information in each node so you can quickly figure out the two elements that give the maximum sum within any queried range. And you can still update elements quickly.
So they're flexible. You build this tree structure on top of your array, and it lets you ask questions about ranges very quickly.
That's the essence of it. Really useful in competitive programming and areas where you need fast range operations.
Okay, one last structure, heaps. What makes them special?
Heaps are another tree-based structure, but they have a specific rule called the heap property. For a min heap, every node's value is smaller than or equal to its children's values. This means the smallest element in the whole heap is always right at the root.
And a max heap is the opposite.
Yeah.
Biggest element at the root.
Exactly. Every node is greater than or equal to its children.
So they're good for quickly finding the minimum or maximum thing.
Perfect for that. And because of this property, they're the standard way to implement priority queues.
Priority queues, like a regular queue, but items come out based on priority, not just first in, first out. Highest priority first or lowest, depending.
That's precisely. Heaps let you efficiently add a new item with a certain priority and efficiently extract the item with the highest or lowest priority. Both operations typically take O log n time.
What's a book example for heaps?
The supermarket promotion problem. A store gives a prize based on the difference between the most expensive and least expensive item on a receipt. You need to process lots of receipts.
Okay.
You can use 2 heaps per receipt as you scan the items, a max heap to keep track of the most expensive items seen so far, and a min heap for the least expensive. When you finish scanning a receipt, the max and min values are instantly available at the roots of the heaps.
Makes finding those extremes really fast.
Very efficient. And the book also briefly mentions that heaps are often used inside Dijkstra's algorithm.
Oh, yeah.
Dijkstra's needs to repeatedly find the unvisited node with the currently smallest known distance. A min heap, used as a priority queue based on distance, is perfect for quickly finding that minimum distance node among all the candidates. It speeds up Dijkstra's considerably on many graphs.
So heaps are all about efficiently managing and retrieving the minimum or maximum element.
That's their core strength. Great for prioritization, scheduling, optimization algorithms like Dijkstra's.
Wow. We've really covered a lot. Hash tables for fast lookups, recursion for trees, DP for optimizing, graphs for networks, union find for groups, binary search for sorted data, segment trees for ranges, heaps for priorities. It's quite a toolkit from algorithmic thinking.
It really is. Each one offers a specific, efficient way to tackle certain kinds of problems. Knowing which tool to use when, that's a big part of algorithmic thinking.
It makes you wonder, doesn't it? How much do these ideas apply outside of just coding? how we organize things or make decisions, using efficiency or hierarchy, or finding the best option.
That's a great question. I mean, the core idea is breaking down complexity, finding structure, seeking efficiency. That sounds like a useful life skill, you know? Even if you're not consciously thinking, this is like Dijkstra's algorithm.
Yeah, the underlying principles seem broadly applicable. Well, this has just been a taste, obviously. The book Algorithmic Thinking goes much deeper with more problems and details.
Definitely worth exploring further if this sparked any interest. Trying out some of the problems is the best way to really get a feel for it.
Absolutely. So what concepts stood out to you today? Or what real-world problems are you now seeing in a slightly more algorithmic light? We'd love to hear your thoughts. Thanks for joining us on this deep dive.